In this section, we're going to take a look at modular arithmetic. Back in the last chapter, when we were looking at equivalence relations, one of the relations we defined was a relation on the integers. And we said that A was related to B if and only if 3 divides A minus B, or if the difference A minus B is divisible by 3. And then we use this notation with this sort of triple equal sign, saying that it's equivalent. Mod 3, and then sometimes people will just use the regular equal sign. They're understood to mean the same thing, but what is really important is that we do include the fact that we're looking at this mod 3. We could define a similar relation for any fixed positive integer and just say that on integers n, we say that a is equivalent to b mod n if and only if n divides the difference, a minus b. And we showed that that was an equivalence relation. And the idea behind this, and here's sort of one big takeaway, and we probably talked about this a little bit before the break, but the idea behind this integer, or behind this relation, is that a and b are equivalent or related if they give the same remainder upon division by n. So, for example, if we look at the relation equivalence mod 5, we're saying that a and b are equivalent mod 5 if a minus b is divisible by 5, or in other words, if a and b give the same remainder upon division by 5. So the set, the equivalence classes would be the set of all the possible remainders when we divide by 5. And that set, well, I could get a remainder of 0, or a remainder of 1, up to a remainder of 4. A remainder of 5 would actually mean I could just take out another 5 and get a remainder of 0. So it's sort of a cycle here. So these are all the possible remainders. And we have some notation for this set. We call it z sub 5, and we usually use like this integers z. There's other ways. Sometimes people will just use a regular z sub 5 or z mod 5z. I tend to stick to this notation here, but either of these notations is acceptable. So this set that we have of all these remainders when we divide by 5, we call it a set of residues mod 5, or the integers mod 5. Like if I look at all the integers and just sort of reduce it by what remainder, by what I get when I take out all the multiples of 5, how many times does 5 go in and what's left over, then that'll just boil down to the set of remainders from 0 through 4. We could do this for any integer n. So, for example, z7, right, the set of remainders mod 7 will be from 0 up to 6. z12, the remainders upon division by 12 go from 0 to 11. And I could do this for any n. So for zn, I'm going to start at 0, and I stop at n minus 1. So the set zn has n integers in it from 0 up to n minus 1. We can do arithmetic on these residues. So we have a set of integers, the integers mod 5 or the integers mod 7. We can do addition and subtraction just like we normally would. We're just going to add the residues together and then in the end reduce mod, in this case in example 510, reduce mod 5. So 3 plus 4 mod 5, that's 7. But when I get a result, it should be, keep in mind that z5 is 0 through 4. So when I'm performing some addition or subtraction, combining a couple elements, I ought to get a result that's in that set already. So I don't see 7 listed, so what I need to do is say, okay, well, what is 7 mod 5? In other words, what's the remainder that I get when I divide 7 by 5? And that remainder is 2. It's 2 more than a multiple of 5. And there's the result there. Now, this other addition, so we have 28 plus 14, so we could do the same thing. This gives us 42. And 40 is a multiple of 5, so this reduces to 2 mod 5 as well. Now, one thing I'd like you to observe here is that 28, if we reduce both of these mod 5, 28 is 3 mod 5. And 14 is equal to 4 mod 5. So this we could have reduced first. When you have an equation that you're working with mod n, you always have the option, and a lot of times it's advisable, to reduce all numbers first if they're not already reduced. And just rewritten this as 28 plus 14 is equal to 3 plus 4 mod 5. And then got our result, which would have put us back here. Now, so there's some addition. When we do some subtraction, we're first going to think of the subtraction b minus a. I'm going to rewrite that as b plus a negative a. That's just a general truth. It's true for all numbers. We can think of subtracting as adding the negative. So that makes our work right now wanting to find the value of negative a in Zn for each of these residues. The value of negative a should be the number that we add to a to get 0, right? A minus a is equal to 0. Like, that's what defines negative a. And whatever negative a is, we call it the additive inverse of a. So, the way that changes for us, or at least how we have to adapt to this idea, or adapt this idea to our new sets, right, to the integers mod 5 or the integers mod 7 or something, is that in example 511 here, whatever negative 3 is has to be one of the values already in the set, right? Z5 contains integers 0 through 4. So whatever negative 3 is going to be one of those. It's going to be equivalent to one of those 5 integers. And it's got to satisfy the equation that when I add it to 3, I get 0. So I'm going to just posit to you right now that negative 3 is equal to 2 mod 5, and I'm going to show you why. Because when I take the value 3, not negative 3, but positive 3, and I add 2, I get 5, and 5 is equal to 0 mod 5. So 2 is the number that I add to 3 to get 0, and that means that negative 3 is equivalent to 2. That's useful for us because that means if I wanted to subtract 3 from anything, that's the same as adding 2 in Z5. So 0 minus 3 is the same as 0 plus 2, which is 2 mod 5. 1 minus 3 is the same as 1 plus 2, which is 3 mod 5. 2 minus 3 is the same as 2 plus 2, which is 4 mod 5. 3 minus 3, well, at this point, I don't know if it is all that helpful to rewrite it as addition because 3 minus 3 is just 0. That's easier to think of it that way. I don't have to go through the extra step. And 4 minus 3, again, I'm just going to keep that as subtraction. That makes it a little bit easier, is 1 mod 5. If you wanted to, you could write this as 4 plus 2, and that's 6, and 6 is equal to 1 mod 5. It's 1 more than a multiple of 5. In essence, the integer Z5, it's like having picture a clock but with only 5 hours on it. And I can sort of rotate these in a rigid fashion. So there's nothing that exists in between the two, right? I'm just going to rotate, and these 5 dots will be in those 5 locations. It's just that where's the 0, where's the 1, where's the 2. And so what we're saying, like, let's take a look at this equation right here, 2 minus 3. So we're saying, suppose we're starting here. What this says is that subtracting 3, so going backwards 3 units, is the same as going forward 2 units. And of course it is. They both land us at the value 4 that we found. In this next example, what is 2 minus 4 mod 5? Well, negative 4 is equal to 1 mod 5. We could see that because 4 plus 1 is 5, which is 0. We could also see that, you know, in our diagram up here, going backwards 4 units is the same as going forward 1 unit. So 2 minus 4 is the same as 2 plus 1, which is 3 mod 5. And we could sort of visualize that here. 2, if I'm starting at 2, then going backwards 4, 1, 2, 3, 4 is the same as going forward 1 unit. It lands us at 3. You may have already noticed this pattern with Z5, but in Zn, like just sort of in your generic Zn, negative a, if a is between 0 and n, then negative a is just n minus a. Subtract a from the modulus itself. So if I want to know what is negative 25 mod 100, negative 25 mod 100 is 100 minus 25, which is 75. It's important that we do indicate the modulus on our equations, at least at the end, because we want to make sure, like, this might not hold for other modulus. So, like, we have to make sure that we're indicating which set of integers that we're working with. Now that we have some addition and subtraction, we could do some really simple equations, the ones that only involve addition and subtraction. So we're gonna get to the multiplication and division in a little bit, but let's say I want to solve for x here, and I know that 5 plus x is equal to 2 mod 7. So look, we're working with Z7. If this equation has a solution, it's going to be one of those values. And if I want to go about solving it algebraically, I would want to subtract 5, right? We all look at that equation and we say, okay, I got to subtract 5. Well, what is negative 5 in Z7? Negative 5 in Z7 is going to be 7 minus 5, or 2. So negative 5 is equivalent to positive 2 mod 7. That means that if I want to subtract 5, that's the same as adding 2. It's convenient to add 2 because it will automatically land me a number on the right side that's between 0 and 7. And 5 plus 2, that's equal to 0 mod 7. So we just get x is equal to 4 mod 7. And you can always check. You know, just like other equations, you can check it. 5 plus 4 is equal to 9, and 9 mod 7, 9 is 2 more than a multiple of 7, so this is 2 mod 7, and that checks out. We're going to, in number theory, you know, I mentioned before that one of the applications of number theory is in encryption, and we're going to see a couple different, I guess if I include this one that we're just going to look at, 3 types of encryption. This encryption is so simple and not, you know, like really probably not secure that I wouldn't imagine anybody actually uses it, but it's the oldest form. It's called the shift cipher or the Caesar cipher. But the idea with encryption is that there's a message that we write down, like the message that we want to send. We call that, the original message is called plain text, and the message that we send, the coded message that has to be deciphered is called ciphertext. If you know the method of encryption, there's in order to encrypt your plain text, you need an encryption key, which just is the instructions for how you encrypt the message. And then if you get a coded message, an encrypted message, you need a decryption key, which tells you how to decode or decrypt the message. So we're going to look at the shift cipher. This is super simple. The idea is, let's say I've got the alphabet A to Z, and I've assigned them integers from 0 to 25. And when with the shift cipher, it is exactly what it sounds like. We're just going to shift each letter down. So let's say we pick a number, and in this example, we're going to pick a shift of 15. Then that means that our encryption key is that we get the ciphertext C by taking the plain text and adding 15, and then reducing mod 26. Reducing mod 26 because we want to make sure we get another letter. Right? If I do the addition and I get something like 32, 32 doesn't correspond directly to one of these values, but once I reduce it mod 26, it will correspond to one of these letters. And we're working mod 26 because we've got the integers from 0 to 25. So let's say we're going to encode the plain text message hello. Right, so here's just these values are what we need. So that means, let's see, hello corresponds to the numbers 7, 4, 11, 11, 14. And I'm just going to encrypt each one of these individually. So the letter E, I'll just go in the order of the alphabet. So E, that's 4. Now I'm going to use my shift cipher, the shift of 15. So 4 plus 15 is 19. 19 corresponds to T. Let's see, next H is 7. 7 plus 15 is 22. And 22 is W. And L is 11. 11 plus 15 is 26. And if I reduce that mod 26, that's 0. And that gives us A. And then O, 14. So I take 14, I add 15, I get 29. Again, reducing mod 26 gives us 3, and 3 is D. And I didn't circle that one before. So again, here we're just reducing mod 26. So 7, 4, 11, 11, 14. Right, when we add 15 and then reduce mod 26, that gives us 22, 19, 0, 0, 3, or WTAAD. So hello encrypts to Watad, if that's how we say that. Not a very secure cipher. If you knew somebody was using the shift cipher, it would just be a really quick guess and check. You could, well, brute force actually just check each, but there's only a shift. You can either shift from 0, which means don't encrypt it at all, up through a shift of 25. So you could just check them all. So nobody actually uses the shift cipher because it's ridiculously insecure, but it's the oldest, probably one of the oldest, if not the oldest type of encryption that has existed. Now, if we wanted to, before we go on to multiplication division, suppose somebody gets the message with Todd, right? They'd have to know what the decryption key is. So ideally, you know, with this type of, we call this like a secret key or a secure key, meaning you have to keep the encryption and decryption key secret. If somebody knows your encryption key, they can tell your decryption key. If I know you shifted it down 15 spaces, 15 letters, I just shift it back the other direction, 15 letters, right? It's easy. So you have to keep your encryption key secret. But if I'm sending it to somebody and I know that they're the only ones who knows the encryption key, and then they want to decrypt it, for the decryption key, first I'm going to start with, here's our encryption key of this equation, right? We took the plain text, we added 15, and then we reduced mod 26. To decrypt, I want to get the plain text P from the ciphertext C, so I'm going to solve that for P. And so I want to subtract 15 from both sides, and if we're working mod 26, subtracting 15 is the same as adding 11. So then C plus 11 is equal to P, or P is equal to C plus 11 mod 26. So if all we have are addition and subtraction, you know, there's not a whole lot of encryption we can do. To make things more interesting, we have to expand out to multiplication and division. So we'll start with multiplication. This is similar. Multiplication is really similar with our approach to addition. We're just going to do the multiplication and then reduce mod whatever. So in 518, we want to know what is 5 times 7 mod 9. Well, 5 times 7 is 35. And if I reduce mod 9, let's see, that'll give us 8 mod 9. That's 8 more than 27. You could also think of it as 1 less than 36. 36 a multiple of 9, so if you're 1 less than a multiple of 9, you must be 8 more than a multiple of 9. But if I did this with mod 10, right, 5 times 7 is still 35, but now I'm going to reduce mod 10. That one's a little easier because multiples of 10 are quick to come up with. This is 5 more than 30, so this is equal to 5 mod 10. Right, so the same idea. Do the operation and then reduce mod whatever, mod 9, mod 10, mod n, whatever your modulus is. To talk about division, the first thing we need to understand is that we don't really have division. What we do have are multiplicative inverses. And having a multiplicative inverse is kind of like having division, but what we have to understand is that multiplicative inverses don't always exist. So division isn't really a well-defined operation in Zn because you can't always do the division. Sometimes you can, and we're going to talk about when you can do that and how to figure it out. But first, let's talk about the real number. So get out of Zn for a second and think about the real number. So when you took pre-calculus or your algebra course or whatever, what is the multiplicative inverse of 2 in the real numbers? So in R, in the real numbers, the multiplicative inverse of 2, which is 2 to the negative 1, is 1/2. And that is because if I take 2 and I multiply it by 1/2, I get 1. This is the idea of a multiplicative inverse. The multiplicative inverse of, in this case, 2, is whatever I multiply by 2 to get 1. Right? 1 is the multiplicative identity. When I multiply something by 1, I don't change it. So finding a multiplicative inverse means I want to know what do I multiply by to get back to that identity, to get back to 1. And so that's what is written right here. The multiplicative inverse of a number a is what you get, is what you multiply by a to get 1. So in the real numbers, a multiplicative inverse is like, we hardly have to think about it at all. If take any real number a, right, as long as it's not 0. If I want to divide by a, meaning if I want to find the multiplicative inverse of a, I'm going to just take 1 divided by a, 1 over a. So dividing by a is the same as multiplying by 1 over a. And that's as long as a is not 0. If a is 0, then it's not defined. So this is the same as saying that the multiplicative inverse of a is 1 over a. Now, so this is what it is in the real numbers. The multiplicative inverse of 5 is 1/5. The multiplicative inverse of 12 is 1/12. Right, it's those fractions. And because we can cancel, right? It's that arithmetic that we know and love. Now, let's get out of that. Let's extend this idea to Zn. So if I want to find the multiplicative inverse of a number, I'm looking for the number I multiply by that value to get back to 1. So first of all, Z5, which I'm just going to write it out again here, 0, 1, 2, 3, 4. The inverse, so we start out with just being told that the multiplicative inverse of 2 is 3, mod 5. And the reason that's true is because 2 times 3, right, the thing I multiplied by 2 to get 1 is 3. That's what they're telling me. 2 times 3 is 6, and 6 is in fact equal to 1 mod 5. And if I'm looking for an inverse, with a pretty small set like Z5, you can just check, right? Just if an inverse exists, it's going to be one of those numbers in Z5. So I just do the multiplication and check, does this give me 1? If it does, it's the inverse, and if it doesn't, then it's not the inverse. Next, it says find the multiplicative inverses of the other residues in Z5. So, okay, let's go down the list for Z5. So we already found that the inverse of 2 is 3. But look, if 2 times 3 is 1, then certainly 3 times 2 is 1, right? So if the inverse of 2 is 3, that means that the inverse of 3 is 2. When you do find inverses, you get to really pick them off in pairs because it's a reciprocal relationship unless a number is its own inverse. 0 does not have an inverse. 0 never has an inverse in any Zn. In fact, not in the real numbers either. The inverse of 1, so if I want to know what do I multiply by 1 to get 1 mod 5, and it's going to be one of the numbers in the list of numbers in Z5 in the first place, that's pretty quickly we can conclude that the inverse of 1 is 1, is its own inverse. And in fact, the inverse of 1 is always 1 in every Zn. The inverse of 4, you can kind of go down the list. 4 times 2 is 8, that's 3 mod 5, not 1. 4 times 3 is 12, that's 2 mod 5, not 1. 4 times 4 is 16, now that's 1 mod 5 because 16 is 1 more than 15, a multiple of 5. So the inverse of 4 is 4. And in fact, in any Zn, the last value is always its own inverse. So we could say that n-1 inverse is equal to n-1 in every Zn. So 1 is always its own inverse. The last value, the last number, is always its own inverse. And I could sort of explain why 4 should be its own inverse, and that extends to n-1 in any Zn. 4 is equal to -1, right? So the inverse, 4 should be its own inverse because -1 times -1 we already know is +1. And that's true for n-1 in any Zn. Now I'm going to do a little bit more here. They don't ask us to do this, but I think it can be helpful and certainly will be helpful on your next assignment that's coming up. So we're going to make a multiplication table for Z5. So we are multiplying, got 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Some of these rows and columns are easy to fill out, like 0 times anything is 0. So there's our first row, and there's our first column. 1 times anything is itself, so there's our second row, and there's our second column. 2 times 2 is 4, that's already reduced mod 5. 2 times 3 is 6, that's 1 mod 5. 2 times 4 is 8, that's 3 mod 5, 3 more than 5. The row for 3 times 2 is 1. 3 times 3 is 9, 9 is 4 mod 5, and 3 times 4 is 12, which is 2 mod 5. And then last, 4 times 2 is 8, which is 3 mod 5. 4 times 3 is 12, which is 2 mod 5. 4 times 4 is 16, that's 1 mod 5. So notice that I did the multiplication, then I reduced. So all the numbers in these squares, or in these boxes, are elements of Zn, are reduced, right? Are chosen from 0 through 4. Now, if I have a multiplication table, I can easily identify, if I want the inverse of 3, for example, I just scan the 3 row, look to see if a 1 shows up. It does, and I say, oh, that happened in the 2 column, so that means that the inverse of 3 is 2. In the assignment that you're going to turn in, you're asked to make a multiplication table for Z7. So now we know how to do sort of division. I put that in quotes because, you know, division isn't really well defined, but we have some multiplicative inverses. So we could solve some more complicated equations. So let's say I want to solve this equation, 3x plus 2 equals 4. This one's a little bit more complicated just because it involves, I have a coefficient other than 1 on x. So 3x plus 2 equals 4 mod 5. So if this has a solution, it's going to be one of the integers in mod 5 from 0 to 4. We're going to do what our instincts tell us to do to solve this linear looking equation, and that is I'm going to get the x by itself. I want to subtract 2, and in this case I'm going to actually write it as minus 2. Just because then my value on the right side will already be reduced mod 5. But equivalently, you could say, because we're in Z5, to add 3 to both sides. So on the left side, we have 3x. On the right side, 4 minus 2 is 2. Now what I really want to do here, you know, our instincts say, oh, let's divide by 3. But we need to find the inverse of 3 mod 5, and we did that on the last page. The inverse of 3 is 2. So what that means is that I want to divide by 3, but I don't have division. I'm going to multiply by 2, both sides. So 2 times 3 is 6, so I get 6x equals 4. But of course, the reason I multiplied by 2 is because I knew it was the inverse. If I reduce 6 mod 5, I just get 1, so we get x equals 4. And in fact, because I knew I picked the inverse, I was guaranteed that this was going to just reduce to plain old x. And so a lot of times people will skip this step here and go straight to the last one, and that's fine. That's good communication. So we get x equals 4 mod 5. Now, we solved an equation. We can check it. We can convince ourselves that this is correct. So 3x plus 2 equals 4 mod 5. Okay, let's put in our solution, which was 4. So 3 times 4 plus 2. That is equal to, let's see, 12 plus 2 is 14 mod 5. And 14 mod 5 is 4, right? It's 4 more than 10, which is a multiple of 5. So that checks out. One thing that makes the Zn integers different than working with real numbers is that the inverses don't always exist. So let's say I wanted to find the multiplicative inverse for each element in Z6. We already know that 0 doesn't have an inverse. 0 never has an inverse. And then, let's see, we're in Z6, so we're going to go up to 5. The other things we know is that 1 is always its own inverse, so I know that's 1. And then the last integer is always its own inverse. So the inverse of 5 is 5. We can check that. 5 times 5 is 25. That's 1 more than 24, which is a multiple of 6. So here's Z6. We know that 0 doesn't have an inverse, so that means it's not going to be the inverse of anything. 1 is its own inverse, so it's not going to be the inverse of anything else. And 5 is its own inverse, so it's not going to be the inverse of anything else. If I'm looking for the inverse of 2, it's going to be one of these three. 2 times 2 is 4, that's not 1 mod 6. 2 times 3 is 6, that's 0 mod 6. And 2 times 4 is 8, which is 2 mod 6. So 2 does not have an inverse. In fact, I think there's a nice way to kind of finish out this problem. Why don't we go ahead and make a multiplication table for Z6. So the first row and column are all zeros. Let's see, multiplying by 1 is pretty easy. Okay, now 2 times 2 is 4, that's already reduced mod 6. 2 times 3 is 6, that's 0 mod 6. 2 times 4 is 8, which is 2 mod 6. And 2 times 5 is 10, which is 4 mod 6. Let's do the 3 row. 3 times 2 is 6, which is 0. 3 times 3 is 9, which is 3. 3 times 4 is 12, that's a multiple of 6, which means that's 0. 3 times 5 is 15. 15 is 3 more than 12, so this is 3 mod 6. The 4 row. 4 times 2 is 8, that's 2 mod 6. 4 times 3 is 12, that's a multiple of 6, so that's 0. 4 times 4 is 16, that is 4 more than 12, 4 more than a multiple of 6. 4 times 5 is 20, which is 2 more than 18, so that's 2 mod 6. 5 times 2, we'll do the last row, 5 times 2 is 10, 10 is 4 mod 6. 5 times 3 is 15, that's 3 more than 12, so it's 3 mod 6. 5 times 4 is 20, that's 2 mod 6, 2 more than 18, and 5 times 5 is 25, which is 1, because it's 1 more than 24. So now, if I'm looking for inverses of 2, 3, and 4, notice there are no 1s. No 1s that appear here. If a 1 doesn't appear in the 2 row, that means 2 doesn't have an inverse. If a 1 doesn't appear in the 3 row, that means 3 doesn't have an inverse, and so on. So 2, 3, and 4, none of them have inverses. So not only do inverses not always exist, but I'm going to just take a minute and point out something kind of interesting. Look at this entry right here. It's not the only one like it. In fact, any of these zeros, you know, that one or that one will work. But like if we focus on this one, this says that 2 times 3 is equal to 0 mod 6, which is true, right? Because it gives you a multiple of 6, and any multiple of 6 is equal to 0 mod 6. In Zn, now it's possible that usually this does not happen in regular algebra that we know and love. 2 and 3 individually, this is going to blow your mind, these are not 0, right? So we have these two non-zero values in Z6. And we multiplied them and we got 0. That never happens in the real numbers. In fact, when we use the fact that in the real numbers, if you multiply two things and get 0, one of them must have been 0. That's one of our techniques for like solving a quadratic by factoring. So this is sort of an interesting set of numbers, Z6. We say that Z6 has 0 divisors. This is just sort of bonus material here. So 2 and 3 are called 0 divisors. And that's just sort of interesting. But again, our focus right now is on inverses, and the other thing that makes Z6 interesting is that not everything has an inverse. In fact, only 1 in 5 have inverses. A theorem on the next page is going to kind of sum up nicely when we know an element of Zn has an inverse. So if A is an element of Zn, then A inverse exists if and only if A and N are relatively prime. So again, remember that means that A and N share no factors other than 1. So going back to this example, of course 2 does not have an inverse because 2 is not relatively prime to 6. Neither is 3 and neither is 4. Right? 6 is divisible by 2 and 3, so clearly it's going to share a factor with 2 and 3, and 4 has a factor of 2, which it shares with 6. They're not relatively prime, so they're not going to have an inverse. We can use this to help us figure out which entries or which elements have inverses, so that if I'm looking for an inverse, I can first just answer, well, does it have one? And if I know it doesn't, then I'm not going to bother looking for it. So in Z8, right, Z8 is integers 0 to 7. So which ones have inverses? They're going to be the ones that are relatively prime to 8. So the ones that have an inverse will be 1, not 2, because 8 is divisible by 2. 8 is just 2 cubed. So anything that's divisible by 2 won't have an inverse. So 1, 3, 5, and 7, those are all relatively prime to 8. Now, what if I want to work with a Zn, and for reasons, I want to make sure that every element, every non-zero element, 0 never has an inverse, but if I just want to make sure that every non-zero element has an inverse, I have to, in order to make that happen, I have to make sure that all the other elements are relatively prime to n. So if I want to make sure that that's the case, right, all these integers less than n are relatively prime to n, the only way to make that happen is if n is prime. If n is prime, then it's not going to share any divisors with 1 up through n minus 1. When a multiplicative inverse does exist, there's not an easy formula to find it. There is a technique, and in fact, we're going to use that technique later on. When we're working with small enough values, we can find the inverse just by doing a little bit of guess and check. And that often, for small enough n, for Zn, for a small enough n, that ends up being probably the easiest way. Later on, we're going to work with really big values when we look at some public key encryption. And when that happens, we're going to go back and see how the extended Euclidean algorithm can help us find an inverse. So let's solve some equations. Let's say I want to solve the equation 3x equals 5 mod 8. So, you know, our instinct here, we see an equation like this, we think, divide by 3. We don't have division, so we're going to look for what is the inverse of 3 mod 8. So Z8, I'm just writing them out because if the inverse exists, then it'll be one of these values. Now notice, okay, we know the inverse exists, right, because we already identified it up there. 3 is relatively prime to 8. There are a bunch of values that don't have inverses, right? And if 2, 4, and 6, and 0 don't have inverses, they're not going to be the inverse for another element. So if 3 has an inverse, it is going to be one of the other values that isn't crossed out. And in fact, we can cross out the other candidates too. 1 is its own inverse, so it's not going to be the inverse of 3. 7 is its own inverse, so it's not going to be the inverse of 3. We've now boiled it down to saying the inverse of 3 is either 3 or 5. And you can just check, right? 3 times 3 is 9. That is 1 mod 8. That's one more than a multiple of 8. So that works. So we're going to multiply by 3 on both sides. 3 times 3x is 9x, or just x, 1x. And we get 15 mod 8. And if we reduce 15 mod 8, that is 7. Let's do another one. Let's say 5x plus 8 is equal to x plus 6. You know, it's linear in nature, so we're going to kind of follow our instincts and say, let's get all of our x's on one side and everything else on the other side. So I'm working mod 9 here. So look, instead of subtracting 8, because I'm working mod 9, I'm going to add 1. I know that if I add 1 here, that's going to give me 9, which is 0. So I'm going to add 1 to this side as well. And then I'm going to actually subtract x. So now I get 4x equals 7 mod 9. Now, to see if we can proceed, what we would want to do is divide by 4. Of course, we know that means we need a multiplicative inverse for 4. Does the inverse of 4 exist in Z9? It does, because 4 is only its prime divisor, only prime divisor is 2. 9 is just divisible by 3. So 4 and 9 are relatively prime, and we just need to figure out, what do I multiply by 4 to get 1 mod 9? So first I'm going to cross out candidates that I know can't be the inverse, like 0. Anything that's not relatively prime to 9, so like 3 and 6. 9 is its own inverse. So that's not going to be the inverse. 1 is its own inverse, so that's not going to be the inverse. So I just need to check these values. 4 times 2 is 8. That's not 1 mod 9. 4 times 4 is 16. 16 is equal to 5 mod 9. 4 times 5 is 20. That's 2 more than 18. So that's 2 mod 9. 4 times 7 is 28. That's 1 more than 27. 27 is a multiple of 9. So the inverse of 4 is 7. Because 4 times 7 is 28, which is 1 mod 9. So I'm going to multiply both sides by 7. Now, 7 times 4x. I chose 7 because it's the inverse of 4, so I know on the left side I'm just going to get plain old x. 7 times 7 is 49. And let's see, the closest multiple of 9 would be 45, and that's 4 more than 45, so this is 4 mod 9. All right, one last example, just to talk a little bit about what happens when the inverse doesn't exist. When you're solving an equation and you find yourself looking for a multiplicative inverse of some value mod n, if you find that the inverse doesn't exist, right, which would happen because it's not relatively prime to the modulus, then one of two things could happen. Either there's no solution at all, or there could be more than one solution to the equation. So the equation 4x equals 7 mod 10 has no solution. And we'll just note, right, that 4 and 10 are not relatively prime, right? The greatest common divisor of 4 and 10 is 2, which is not 1. So that means that 4 inverse does not exist in Z10. So you could check them all. You know, this is easy to check by brute force, by the way, because Z10 just has the values from 0 to 9, and you could just plug all 10 of those in and see that it doesn't work. But if I look at this equation, 4x equals 6 mod 10. Now 4 still doesn't have an inverse, mod 10, right? They're not relatively prime. But as it turns out, there are two solutions to this. So one solution is x equals 4, because, let's see what happens when we plug it in. 4 times 4 is 16, and that is 6 mod 10. The other solution is x equals 9, because 4 times 9 is 36, and that is also 6 more than a multiple of 10, so that's 6 mod 10. All right, so this was a big section, right? We're learning this modular arithmetic. It can be tricky, especially once we start talking about finding the inverses. I would encourage you to do the practice exercises, encourage you to please reach out with questions and come to the office hours that I'm going to be holding on Zoom. I will send out announcements before office hours, but I'll hold them at least once a week, probably at a usual class time.